My name is Silverberg. I'm going to show you some of the physics of origami that we've been exploring here in the Cohen lab at Cornell University. The bottom line is this. If I take a sheet of paper and put a fold pattern in it, I can turn that paper into a spring. If I change the fold angles, I can change the springiness of this structure. The really cool thing about origami is that I can actually activate new creases on the fly, dynamically changing the stiffness of the structure. So it looks something like this. For now, I have a stiffer spring. In this video, I'm going to show you how to make one of these for yourself so you can explore these ideas on your own. This pattern is known as the Miura-ori. We're going to start with the unfolded sheet on the left and end with the folded sheet on the right. The Miura-ori is an origami tessellation. Here, I've cut out a single unit from the corner and folded it to show the relationship between individual units and the structure as a whole. The reason we study the Miura-ori is because it's an example of what we call a mechanical metamaterial. We'll get to that later. For now, let's make one. Start with your crease pattern oriented like this. The red and blue lines indicate where creases go and what direction they'll be folded. Red lines are mountains, which come up at you. Blue lines are valleys, which go away from you. Rather than fold along every individual mountain and valley crease, I'm going to show you a trick that saves a lot of time and effort. Start by folding all the horizontal lines, kind of like an accordion. You'll notice that some of the mountains are folded as valleys, and some of the valleys are folded as mountains. For right now, that's okay. By the time we're done, all of this will be corrected. Next, we're going to fold on these diagonals, back and forth, just like this. Again, some of the mountains are valleys, some of the valleys are mountains, and again, all of this will be fixed by the time we're done. Now, unfold things and come back to this partial accordion-like structure. Move to the first row and start popping the mountains and valleys into their proper configuration. You'll see that as you move along the first row, the structure will just sort of hold the pattern by itself. Once you come across, you'll notice that you can start to collapse everything. Once you fold it all the way flat, you'll see that you've introduced a zigzag where that first row was. Repeat this process for the next row, and the next row, and the next row. By the time you're done, you'll end up with a full-blown Miura-ori. One tip is to pay attention to the individual vertices, that is, the places where the creases intersect. You'll see that small errors will start to make the structure look asymmetrical. You can pretty easily fix this by moving and adjusting each crease individually. It shouldn't be a problem, and by the time you're done, you'll end up with a very beautiful symmetric structure. Let's come back to the idea of mechanical metamaterials. In general, metamaterials are made from tessellations of smaller units, just like the Miura-ori we just folded. By setting the folding angles of each individual unit cell, we can change the overall collective springiness of the tessellation. Go ahead and squeeze your Miura-ori back and forth. You'll feel it has some kind of spring-like behavior. This is the idea of a mechanical metamaterial. That springiness is a function of the angles in your fold pattern. What's unique about the Miura-ori and other origami-based mechanical metamaterials is that they're reprogrammable. What I mean by this is that we can change the springiness by introducing pop-through defects like this. Each pop-through defect changes the stiffness of the lattice, making it stiffer. When I said that this was a reprogrammable mechanical metamaterial, the fact that I can pick a pattern of defects to program the stiffness, remove those defects to reprogram the stiffness, and then reprogram this over and over again is the idea of programmability in a mechanical metamaterial. While individual defects can be placed in the Miura-ori to increase its stiffness, pairs of defects can interact in surprising ways. For example, if I add a second defect here and compress the Miura-ori, what we find is that these two defects cancel each other out. As with all configurations, this is entirely reversible. In other words, I'm going to reprogram the stiffness of the Miura-ori back to its original configuration by removing the defects. See? Here we are, back to where we started. Long term, the goal is to incorporate these types of ideas into more complex devices. This will lead to materials that have on-the-fly transformation of their mechanical function. We envision these origami-inspired materials to lead to things like shells that harden on demand, joints that lock in, and barriers that can be instantly deployable. Ultimately, this type of transformer technology will revolutionize the way we think about materials, moving them beyond their current static form and revealing more functionality than we ever thought would be possible with just a simple sheet.